Find the largest real root of the function f of x. In this problem, we've been provided a third-degree polynomial f of x, which will have at most 3 real roots, and we're asked to find the largest of these 3 roots. If the function has only one real root, then the answer will be that one real root. We're instructed to use Newton's method to solve for the root, which requires an initial approximation of the root, xn. Using this approximation, as well as the given function f of x and the derivative of the given function f prime of x, Newton's method will provide us with a new approximation of the root, xn plus 1. Looking at the graph, if we focus in on our root and choose an initial approximation of the root, xn, then the Newton's method approximates the next root, xn plus 1, by drawing a vertical line from xn to the function evaluated at xn. Then, a tangent is drawn from fxn, and wherever that tangent intersects the x-axis will be the next approximation of the root, xn plus 1. Newton's method will work if our initial approximation of the root is close enough to the actual root. If our initial approximation was further away, then Newton's method may not converge as we would expect it to. Before we can begin, we still need to determine the derivative of f of x, f prime of x. And we also need to start with an initial value of x, xn. From calculus, the derivative of f of x equals 3x squared minus 6x minus 160. Now we can revise our equation for x n plus 1 by plugging in the functions f of x and f prime of x. For our initial approximation of x, we'll choose a value slightly greater than the local minimum to ensure the subsequent approximation of the root is in the direction of the actual root. We'll define the point xlm as the x value of the local minimum, which we can find by setting f prime x equal to 0 and solving for the x, and confirming that this value of x also has a positive second derivative. The roots of the quadratic equation are negative 6.37 and 8.37. We'll check the larger value, 8.37, for its second derivative, which is, indeed, a positive value. Since 8.37 is our local minimum, we'll choose xn to be slightly larger. We'll use xn equals 9. Returning to our equation for xn plus 1, we'll plug in 9 for xn, and our value for xn plus 1 equals 20.38. If we set up a table, we can track our approximations of the root as they converge on the actual root. So far, we have our first two approximations, x1 and x2. To get our next approximation, we'll plug in 20.38 for xn, which makes xn plus 1 equal to 15.63. If we continue this process for a few more iterations, we notice our approximation of the root converges on 12, which is the largest real root of the function f of x. When reviewing the possible solutions, the answer is A.